Okay, so here we still have two additional examples to finish off chapter 30. Okay, so this is the first one. So it says a non-coaxial cable consists of two thin wall concentric conducting cylinders with radii A and B. Okay, so this is also coaxial cable, means 同轴. If you still remember, okay, these two cylinders have the same axis. The axis is going through the center of the cylinder and then also perpendicular to the cross section. Okay, so they are called coaxial. So which means that these two cylinders have the same axis. Okay, yeah, and then the inner cylinder carries a static current I. Okay, going a static current I, and then the outer cylinder provides the return path for the current. Okay, so this is for transmitting high frequency signal, so that we need this is transmitting the signal, and then this is like the ground, but the high frequency signal can go back from the outer ring, so it can make a higher frequency signal can go through. Okay, and then current set up and then the current set up a magnetic field between the two cylinders. What okay, this is question A. So calculate the energy stored in the magnetic field for the length L of the cable. Okay, so so what we know is the radius A and B. So the smaller one is A, the larger one is B, and then also the current I. Going maybe out of the page, or either way. So and the outer blah blah blah. So calculate the energy stored in the magnetic field. Okay, so first of all, we would like to consider the Ampere's law for this. This is not Gaussian surface. This is Amperean loop. Yeah. As much as we need to use the Ampere's law, we need to define the Amperean loop. So this dotted line means the Amperean loop. So here we can write out the Ampere's law. So integration of B dot ds equals mu naught I enclosed. Okay, which is actually mu zero I. So because this static current is I. Okay, so as what we have done before, this is nothing but B times 2 pi r. Because it is uniform, it is also, the B is also parallel to the S and with the same direction. So this is simplified to a multiple of between B and 2 pi r. So this is the length of a ds, and also B is a uniform B field over this path. Okay, so this is equal to mu 0 I. So we will have B equals mu 0 I over 2 pi r. Actually, this is what we got before. Yeah, what we got before. And then here we would like to calculate the UB, small ub. So this is the energy density, which will be B squared over 2 mu naught. This is the energy density. So we can plug in this one to here. So we will get mu 0 square I square over 4 pi r square times 1 over 2 pi, 2 mu naught. Okay, so we can do some cancellation. This square cancel with this mu naught. Okay, and that's it. So we have 8 pi, here it should be a square. Okay, so 8 pi square r square. And then here we have a mu naught I square. Okay, so this is UB. Okay, then we would like to calculate dUB. Okay, this is a capital U. This is a capital U means the energy rather than the energy density. Okay, so this is UB times dV. Okay, this is the volume, the small volume around here. So which means that this is actually this ring. Sorry. Maybe I use this one. So which means that dV means the volume here, the volume here. So actually this is a cylinder. So which is like this is just the height of it multiplied by the cross-section area. So this dV. Okay, so here we can just put in UB, small ub here, which is mu0 I square over 8 pi square r square. And then dV for this one is the cylindrical coordinate. Cylindrical coordinate, it should be like r dr d theta dz. Okay, so for this part, it is like the polar coordinate. And then multiply by the c-axis. C-axis is like the independent one. Originally, if it is in Cartesian coordinate, dV should be like dx, dy, dz. Okay, in the Cartesian coordinate. Don't know how to draw a 3D cube. 3D cube should be like this. Okay. So if it is in Cartesian coordinate, x, y, z, z. So this is a dx, dy, dz. Okay, so this is the dV in the Cartesian coordinate. But yeah, in cylindrical coordinate, it would be like two axes of polar coordinate with the z-axis perpendicular to it, and then so it will be this one refer to the polar coordinate. This is the z-axis. Okay, so actually UB will be like integration of dUB. So it is like mu0 I square over 8 pi square. Okay, so referring to this one, and this one. Okay, this r square is related to this one, so we cannot put it out. So inside the integration, we should have this r square and then this r. This r is in the numerator, this is in the denominator. So when they multiply together, it becomes dr over r. And then we integrate from a to b. From a to b, we should be integrate from here to up to here. So we integrate r from a to b. And then for theta, it should be integrate from 0 to 2 pi. And then for dz should be something like 0 to L, something like that. Okay, so in that case, this is lateral log of b over a. Okay, because this is lateral log of r, and then we evaluate from a to b. It becomes lateral log of b minus lateral log of a. It becomes lateral log of b over a. And this one is nothing but 2 pi. This is nothing but L. L is the length. L is the length of the coaxial cable. So altogether, we will have mu0 I square, mu0 I square over, we can see this 8 pi square, and then this pi and pi square can be partly cancelled. This one and this one can also be partly cancelled. So we will have 4 pi here. We have 4 pi here. And then we have this L. So we just put it here, this L. And then we also have this natural log of b over a. So this is the general expression to to the energy stored in the magnetic field. Okay, so for part B, it asks you what is the stored energy per unit length of the cable if A equals 1.2 millimeter square and B equals this value, I is this value. Okay, so actually we just need to plug in all the numbers into here. So I think we can just, let me see. This one, okay. Yeah, you can just put it somewhere. Okay, so we can make use of it. Okay, so actually we have this one, UB to be this expression. So which means that if we just put L to the left side, we will have UB over L, because it asks you the stored energy per unit length. So we have UB over L here. So which will be mu naught over 4 pi and then times I square L, no L anymore, and then lateral log of B over A. Okay, so this one is nothing but 10 to negative 7, and then times I square is 2.7 square, and then natural log of B over A. So it will be 3.5 over 1.2. Both are millimeter square, so they will be cancelled. And then finally, this number will be 7.8 times 10 to negative 7 joule per meter. Yeah, because the SI unit for the energy should be joule, and then SI unit for the length will be meter. So the SI unit will be joule per meter. Okay, so this is the answer. So here we just make use of calculus to calculate the energy stored in between here. Because yeah, there are some as much as there are some current going through there, it will generate some B field in between, which means that it will store some energy. So we make use of a calculus to calculate the energy stored in between, and then yeah, this is actually the energy per unit length here. Okay, so we can put this away. Okay, so next, this is the next additional example. So it says two parallel loops of wire have a common axis. Okay, so this wire and this wire have a common axis, which means that the axis also go through the center and then perpendicular to this circle. Okay, so the smaller loop of radius small r is above the larger loop by a distance. This is x, the distance between them. And then consequently, the magnetic field due to the clockwise current I in the larger loop is nearly uniform through the smaller loop. Okay, so here it tells you that for the larger loop, it has a current going counterclockwise. Okay, and of course, this counterclockwise current, it is just like a magnetic dipole, so it will generate some B field. Of course, not so uniform, but here it assumes that this x is much larger than r, so that we assume that the magnetic field going through is nearly uniform through the smaller loop. We assume that the B field here is uniform. Of course, it is not so. But if we assume that x is much larger than r, then we can approximate it to be uniform. So we just pick B at the center point. We may be easy to calculate, but we may not be able to easily to calculate the B field at here. But yeah, we just do this approximation so that it's just like we have this B at the center and then multiply by the cross-section area to make the magnetic flux calculation easy. Or or possible to be hand calculated. Okay, so here it asks you, suppose that x is increasing at the constant rate v equals dx dt, which means that this x is increasing. Which means that this one is moving upward, or maybe this one is stable. This one is moving upward with a constant velocity v, a constant speed. Okay, find an expression for the magnetic flux through the area of the small loop as a function of x. Okay, so before in chapter 29, we know that if we have a magnetic dipole and then along the z-axis, if z is much larger than, if z is, if x, at that time we are using z for just say this one is a magnetic dipole with a current I, and then this is the z-axis. Okay, so the expression will look like this. So here we have the axis to be x, so we just change z to x. At that time we assume that suppose this is r, and if this is z. If z is much larger than r, we can do some simplification, making it look like this. Otherwise, in the denominator, it will have a square root of something like z squared plus r squared square root, and then to the 3/2 to the third power. Yeah, but here we assume that z is much larger than r, so the expression is simply look like this. Okay, so here we would like to change z to x so that to fit this variable. Okay, so here we have b equals to mu 0 over 2 pi, and then mu vector over x cubed, or actually this mu, or maybe we just sorry okay, so actually this is the magnetic dipole. Magnetic dipole. If you still remember, it should be like mu equals to NIA. N is the number of turn, and then I is the current, A is the cross-section area. Here we only have one turn, so N is 1, so it is I times A. A is the cross-section area, so this is a circle, so it's nothing but pi r square. So it is I pi r square, and then pointing to the positive x-axis. So we use I hat to represent the unit vector in x-axis. Okay, so this is vector B at this point, but we approximate all the B field across or over this smaller loop is constant. Okay, so here we just approximate phi B to be B times A. So this A is different from that A. This A is for the larger loop. Maybe we just put it like AL, and this is the smaller one. So B times AS. So B is nothing but mu 0 over 2 pi times I pi r square, and then over x cubed, and then times AS is pi small r square. Okay, we just drop out all the vectors because we already know that B and AS, B and DAS is parallel to each other, so they point to the same direction. So the dot product is nothing but the multiply of the magnitude. Okay, so this is B, this is AS. Okay, so we can try to collect some of the common terms. Let me see. Pi. Okay, so here we can do some cancellation. We have pi here, so we can cancel with this pi, and actually we don't have any further same term, so yeah, so it will look like this is pi, and then mu naught, and then with I here, and then capital R square, small r square in the numerator, and then in the denominator we have 2x cubed. So this is just some algebraic calculation. Okay, so this is not that difficult. So phi b is this one. So this is the answer to question A. So it asks you the magnetic flux through the area of a smaller loop as a function of x. So this is a function of x. All the other variables are constant. Okay, so we'll make use of this expression. Okay, so here it asks you find the expression of the induced EMF and the direction of the induced current. Okay, so you can simply imagine after we calculate the magnetic flux, so we can calculate the EMF by Faraday's law, which is E equals negative d phi b dt. So we can just plug in the expression here. Okay, pi mu naught I r square over 2x cubed. Okay, so most of the terms are constant, so we can just put it outside. Pi mu naught I small r square capital R square over 2, and then the remaining one is dt, and then 1 over x cubed. Okay, this one is a function of time, because in the question it tells you that v equals dx dt. So for different time x is different. X is actually increasing with a constant speed v. Okay, so we can actually calculate this one using the chain rule. Okay, so this is nothing but negative pi mu 0 I r square capital R square over 2, and then chain rule. So it means that it should be like, so this is 1 over x cubed, which is like h to the negative 3, and then dt. So this is a polynomial, x to the negative 3. So for the derivative, you need to minus 1 to the exponent. So it becomes x to the negative 4th power. And then you multiply by this exponent, negative 3. And then remaining is that you need the chain rule, because this is not t. So you still need a dx dt. Okay, so this is a derivative of this one. And then this is the chain rule. This is due to the chain rule. Okay, so this whole thing is this one. Okay, so finally we can get the expression E to be 3. Okay, so here we have a negative sign, we have another negative sign, so it becomes a positive value. So we have 3 pi mu naught I r square capital R square over 2x to the 4th power. This is nothing but v. So this is v. Okay, so this is the answer to part B. So this is the induced EMF. Okay, so the third question is, what is the direction? So actually you can determine by the polarity of the answer. This is positive. So this is the positive direction. And then using the right hand rule, you use your thumb pointing upward. So this should be counterclockwise also. This is I induced. Or if you try to determine with another way using the Lenz's law, okay, you can imagine we have this current going clockwise, which means that this B field is pointing upward, and actually this one is moving upward. moving upward. So which means that this B is decreasing. This B is decreasing. So B is decreasing. If B is decreasing, according to the Lenz's law, the B induced should be pointing upward. B induced should be pointing upward to cancel this, to try to cancel this change. So B is pointing upward, which means that the current is counterclockwise. So for part C, I induced is counterclockwise. Counterclockwise. Okay, so this is, yeah, so this is it. So